Hey everyone, so today's lesson is on gas stoichiometry. The good thing about gas stoichiometry is that it's pretty much the same as regular stoichiometry, it just has a different last step. So the first step, balance the equation. Second step, we convert either grams, liters, or molecules to moles. Third step, we set up our mole ratio, and the only difference really is our last step, where we'll plug that moles either into PV equals nRT, or we'll just change it to liters using that 22.4 from STP. Remember, a stoichiometry problem is just going from an amount of one compound to an amount of another compound. So in some problems we might be going from liters of CO2 to maybe liters of O2, or we'll be going from grams of methane to liters of oxygen. Okay, so that is what we're going to be doing today. We're going to be using our previous knowledge of gas stoichiometry, our previous knowledge of STP and the ideal gas law in order to solve stoichiometry problems that involve gases. So let's go ahead, let's jot down these steps, and let's check out our first example. So here is our first example. As you see here, I gave you an equation up top, and I'm asking how many liters of water can be produced from 16 grams of oxygen gas at STP. First thing I should note is that I know this is a stoichiometry problem because I start with 16 grams of oxygen gas, and it wants me to get to liters of water. I'm going from one compound to a totally different compound. So this is stoichiometry. So first thing I'm going to do is I'm going to follow my steps of stoichiometry. Let's make sure that my equation is balanced. 2 hydrogens, 2 oxygens, and I got 2 hydrogens and 1 oxygen over there. So let's put 2 here, so now I got 2 oxygens, 2 oxygens. But when I put that 2 there, I now have 4 hydrogens. So I'm going to put a 2 there to get 4 hydrogens. Step 1, done. Step 2, we got to convert it to moles, right? Whatever it may be. Well, always start with what you're given. They gave me 16 grams of O2. Well, I got to change that to moles. And the way I do that, since that's in grams, I'm going to divide by the molar mass of oxygen, which is 32. Oxygen gas is O2, so divide by 32. Now I have 0.5 moles of O2. Step 2 is done. Step 3, mole ratio. I use my multiplication dot fraction bar. What I have goes on bottom. I got moles of O2, so let's put O2 on bottom. And what I want goes on top. Remember, we are looking for how many liters of water. So I'm going to put H2O on top. And then whatever numbers go here is just the numbers in my equation. I got a 1 here in front of O2, a 2 up here in front of H2O. So now I no longer have 0.5 moles of O2. I now have 1 mole of H2O. And then our last step, right? Our last step, we're going to plug it either into Pivnert or we're just going to change it to liters. This is not a Pivnert problem. If it were a Pivnert problem, they would have gave you pressure, they would have gave you a volume, or they would have given you a temperature, or a combination of all those. In this case, they just want liters of water, and the thing that kind of tells me that I'm just converting this to liters is that it's at STP, right? Whenever you see STP, you know at some point you're probably going to be using 22.4. So all we got to do is we got to change this to liters, and since it's at STP, we know that to go from moles to liters, we just multiply by 22.4. Because at STP, for every 1 mole of gas we have, there's 22.4 liters of it. So that 16 grams of oxygen gas is going to produce 22.4 liters of H2O. Let's go ahead and let's do another type of problem. Okay, so we got another problem here where it's asking how many liters of water can be made from 64 grams of oxygen gas at a pressure of 2 atm and a temp of 30 degrees Celsius. So you're probably looking at this problem and you're saying, okay, it wants liters, so it wants volume. It gave me a mass, right, which I could always change to moles, which we'll do later. It gave me a pressure at 2 atm, and it gave me a temperature, okay, which is at 30 degrees Celsius. And you might be saying, hey, P, V, N, T, I know R. This is probably an ideal gas law problem. So if I wanted to, I could plug all this in and I could probably solve for volume here. But we gotta look at the problem. Remember, it's asking how many liters of water can be made. They didn't give you grams of water. They gave you grams of oxygen gas. So yeah, we might want to do this ideal gas law, but we can't do it yet. We need to get that moles of water. Once we get moles of water, then we could plug it into PV equals nRT and find the volume. So what this is looking like, it looks like they gave us gram of oxygen gas, but we want liters of water. So it looks like we're going to have to be using some stoichiometry here. So let's go ahead and let's do that. Let's go ahead and let's solve for this guy. Let's balance it. I just left it balanced because we did it last time. So step 2, we're going from grams to moles, or whatever they give us to moles. But in this case, they gave us 64 grams of oxygen gas. So we're going to get that to moles, which we divide by 32, or the molar mass of oxygen. So we have 2 moles of O2. Step 2 is done. Step 3, mole ratio time. What we have on bottom, what we want on top, how many liters of water? H2O. And once again, this is a 2-to-1 ratio. So now every 2 moles of water will create 4 moles of H2O. And now we're on to step 4, which is convert it back to desired product. And some of you at this stage might be like, hey, I'll just times it by 22.4. This isn't at STP. Remember that STP is at 273 degrees Kelvin and 1 ATM. This is at 2 ATM and at 30 degrees Celsius, which is not 273 degrees Kelvin. So we can't just multiply this by 22.4. It's not a STP, but luckily they gave us pressure and temperature, so we could just go ahead and plug this into PV equals nRT instead. We got pressure, we want volume, we just found moles, we know R because it's a constant, and we could always change 30 degrees Celsius to Kelvin. So let's go ahead, let's do that. Pressure, like I said before, is 2 ATM. Volume, we want liters, right? That's what volume is, so that's what we're looking for. N is moles, which is 4. We just found that using stoichiometry. R is our rate constant, which is 0.08206. Not a rate constant, it's just a constant. And T, right, is in Kelvin, which we got 30 degrees Celsius. We got to add 273 to get Kelvin, which is 303. Which was an old band that none of you probably remember the name or have even heard of. So now we got to get volume by itself. Divide by 2 on both sides. And that will give us volume. Let's go ahead and plug this in. 4 times 0.0. I said 4 times 0.08206 times 303. And then I'll divide that by 2. And I'll get a volume of 49.73 liters. Okay. So that is gas stoichiometry in the case where we plug it into PV equals nRT. You see a situation, again, it wants liters of water, but you have oxygen gas. You might say, hey, we could just change this to liters at the end by timesing it by 22.4. Unfortunately, it's not a STP, so this is where we'd have to plug it into PV equals nRT. Let's go ahead and let's do another example. Same type of reaction, but this case I want to know how many liters of water can be made from 16 grams of O2 and 10 grams of H2 gas at STP. So again, I look at this problem. It wants liters of water, but it only gave me grams of O2 and grams of H2. So I'm going from one compound to another. So I'm thinking stoichiometry. So I'm going to balance the equation. I got it already balanced. No need to balance it more than once. But now we gotta go grams to moles. But here they gave me grams of 2 compounds, not just 1. So now that they gave me grams of 2 compounds, you gotta be thinking, okay, I gotta figure out which one runs out first. I gotta figure out which one is the limiting reactant. So in this situation, I gave you 2 masses. I kind of gave you 2 stoichiometry problems. So we can't just pick one. We have to figure out which one's going to run out first. So let's go ahead and let's do that. We got 16 grams of O2 and we got 10 grams of H2. So we're still in step 2. We got to change these to moles. So we'll divide by the molar mass of each of these. Oxygen is 32, hydrogen is 2. So now I have 0.5 moles of O2, and I got 5 moles of H2. And you might be saying, which one's the limiting reactant? No, you don't do that yet. You got to do the mole ratio, or step 3. What we have goes on bottom, so O2 on bottom. What we want goes on top. How many liters of water? So H2O on top. Same deal here, but instead of O2 on the bottom, it's H2 on the bottom. For top one, it's still a 2-to-1 ratio. For this one on bottom, it is a 2-to-2 ratio. So here it's 1 mole of O2, and this is 5 moles, not O2, sorry, of H2O, and 5 moles of H2O. So which one is our limiting reactant? O2. It ran out first. It's got the smallest amount of moles. It's going to run out first, so we don't care. Remember, get rid of the large one. So now we have 1 mole of H2O. If this wasn't at STP, they would probably give us enough information to plug it into the ideal gas law. But here, since it's at STP, it's simple. We want to get to liters. We just take that 1 mole of H2O and we multiply it by 22.4. So once again, we have 22.4 liters of H2O, right? So at that STP, we could go ahead and do that, since if it wasn't at STP and they gave us a different pressure and a different temperature, we would have to do PV equals nRT. One more example, and then I'm done. So last problem, same equation, says how many liters of oxygen gas do you need to produce 20 grams of H2O at 3 atm and 273 degrees Kelvin. So once again, it wants liters of oxygen gas, but I didn't give you anything to help you get to liters of oxygen gas. I just gave you 20 grams of H2O at a certain pressure and temperature. So I gave you H2O, you want liters of oxygen gas. So we're going to be doing stoichiometry. You guessed it. Equation's already balanced. Let's go ahead and start with what we're given, which they gave us 20 grams of H2O. And let's convert that to moles. We're going to divide by 18 grams per mole. So that is water. Going from one compound to another. 20 divided by 18 is 1.11 moles of H2O. But moles of water isn't going to help us, right? I want liters of oxygen gas. So I'm going to be doing a mole ratio here to get to moles of oxygen. What we have goes on bottom. What we want goes on top. It is a 2-to-1 ratio. So 1.11 divided by 2 is 0.555 moles of oxygen gas. Now, if this was at STP, I could just multiply it by 22.4, and then I'd have my liters of oxygen gas. But I don't have it at STP. It gave us a weird pressure. That temperature's the standard temperature, but that is not the standard pressure. So, in this situation, we're going to have to use PV equals nRT. Pressure is 3. Volume is what we're looking for, right? How many liters? That's volume. N is moles, which we just solved for. It was 0.555. R is that rate, not the rate constant, the constant. of 0.08206, and our temperature is 273 degrees Kelvin. Get volume by itself by dividing by 3. And let's see what we get after we plug this in. 0.08, our calculator. 6 times 273 divided by 3. Looks like we're going to need a volume of 4.14 liters. Okay? That is gas stoichiometry. Just like regular stoichiometry, it's just at the end, you're either plugging it into PivNert or you're multiplying it by 22.4 if it's at STP. Check out the practice. Let me know if you have any questions, and have yourselves a great day.